Good day, everyone, and welcome to the last session of Overview of Multistage Completions for Hydraulic Fracturing course with Engineer Aaron Burton. My name is Jamila, and I am pursuing my bachelor's degree in petroleum engineering at French Azerbaijani University. And today I'm your moderator for this session. First of all, I would like to introduce our special guest, Engineer Aaron Burton. His career has been focused on completion of shales and similar unconventional plays that require multi-stage hydraulic fracturing. In 2015, Burton started Unconventional Oil and Gas Training, a company specializing in training and consulting for unconventional multi-stage completion. Unconventional oil and gas training provides in-house and video-on-demand training courses and performs projects including market studies, due intelligence, reports on specific tool segment, and other projects. He also remains an active instructor and participant in industry. Now I want to remind an information about course itself. It consists of 4 webinars. Today is the last one. There will be a last quiz after webinar and the final exam on Tuesday, 27th October at 2 p.m. and 8 p.m. Egypt time. Please don't hesitate to ask your questions to Engineer Burton regarding today's session in question and answer section. I will read them out in the end. In case of any problem, you can approach me in chat box. And now I ask you to give all your attention to our speaker. Mr. Burton, we are so honored to welcome you today.
Thank you, Jamila. Appreciate it. And thank you, everybody, for joining again. If this is your first day, be sure to go back and review the first 3 days. We've covered a lot of ground here. And in today's module, we'll be looking at refrac and completion selection and comparison. So before we get started, I do want to remind you about some additional resources. So first and foremost, you can check out my website. I have my video blog there and training courses, including some free training courses at uog.training. Some additional material that is not covered in this class as well. And also, if you're watching this, especially if you're watching it on YouTube, please be sure to switch over to my channel real quick and subscribe to my YouTube channel. I'll remember to put the link in the comments so it'll be an easy selection for you there. So if you're enjoying the content, you're interested in this content, please be sure to check out both of those resources. So let's go through refracturing really quick. This is a shortened down version of the refracturing section, but what we're going to focus on is really the tools and techniques that we have here. So this, by the way, this session will probably go a little bit over an hour, especially when it comes to completion comparison. I can get long-winded, but I'll try to keep it short and concise and hopefully useful. So when refracturing is a very interesting topic because it kind of comes and goes. Before the 2015 downturn, it was a very hot topic. Then it slowed down a little bit. Then it kind of came back, and now it's slowed down a little bit more. But there's always interest in it. So let's look at the considerations for refracturing first off. And especially when it comes to downturns, 2015, our current downturn, the main question is how much does it cost? If you look at unconventional wells, they're a little bit different than a lot of conventional completions because, in a lot of conventional plays, drilling can be 70, 80, 90% of the overall well cost, whereas unconventionals, it's about a 50-50 split. And in some cases, the completion cost can actually be higher than the drilling cost. But if we just assume it's a 50-50 split, you still have that level of uncertainty as far as will the refrac work? A lot of the uncertainty revolves around why did the production decline in the first place? It's very difficult to kind of pinpoint that, which also makes it difficult to determine the likelihood of success with refracturing as well. So those are kind of the unknowns with production results. So the main question really and truly revolves around production decline. which can be anything from proppant crushing to proppant embedment to scale, things like that. And the reality is the best we can do is make an educated guess, but that is what it is. It's still a guess in most cases. So we're learning a little bit more about these plays, and it'll be very interesting to see what evolves. But overall, at least from what I'm seeing on my end, the discussion right now in October of 2020, refracturing discussions are still happening, but refracturing activity is not happening as much. And kind of my general observation when I talk to operators about this is when we hit steep downturns like we're having right now, when we hit in 2015, the operators are just a little bit more risk averse. So they look at it and they say, well, theoretically, I could probably refrac a well at 50% of the cost of a new well, but I don't know what the results are going to be. I could get no results and waste that money. But if I drill a new well in a formation that I know pretty well, I have a pretty good idea of what my production is going to look like. So they kind of take the mentality of let's just drill a new well, fracture a new well, and get relatively competent results. I expect that to change in the coming years as we learn more about refracturing, as we're more confident in it. And I think this will be a big topic going forward, especially as the industry recovers. So we'll jump right into refracturing methodologies. So really and truly, one of the main challenges with refracturing is the fact that we have created permanent holes in all of these well bores, or at least most of them, in the form of either perforations or frac sleeves that are not reclosable. So that's the challenge, is how do we re-isolate to get that multi-stage isolation that we got in the original completion system. So far, really one of the more common ways that operators have attempted refrac has been diverters. And this is very similar to the intra-stage diversion that we looked at with plug and perf, except for instead of 6 to 12 clusters in an individual stage, now you may be looking at hundreds of clusters throughout an entire well bore. And we kind of know that it's a grossly simple, grossly oversimplified assumption. But for the most part, operators just kind of assume they place one big frac job down this well bore with multiple holes, and they have to assume that most of the fluid and proppant are going out of one set of perforations. So they'll pump the fluid and diverter, the fluid and the proppant that they want for that individual section, and then they'll pump enough diverter to block off near well bore and force the fluid to divert out of another set of perforations. And just kind of as an added comment here, these perforations may not be just the original completion perforation. So let's say if you went back to a well that was 10 years old in the US, the perforations may have been spaced out 200 feet apart, whereas modern completions, they're typically 20 feet, give or take. So if they go into one of those wells where each perforation is 200 feet apart, they may go in and run a bunch of wireline runs and add perforations to the well. So you may actually be trying to stimulate new perforations as well as old ones from the original completion. So once you pump down that other diverter, it forces the fluid to divert into yet another perforation, and then they just repeat that process. So like I said, it is a grossly oversimplified assumption to kind of visualize it this way. But, outside of just kind of adjusting based on what they're seeing as far as pressures during the refrac, that's about all they can do, is make an educated guess and make certain assumptions. So overall, the upfront cost is relatively cheap for diverters, and it's relatively simple. But the uncertainty is, how well are you distributing your refrac? Now, another technique is straddle isolation, and there's a couple of different ways to do this. It can be as simple as isolation cups. So if you're familiar with swab cups, it's essentially the same thing. You just have an upward facing cup and a downward facing cup, and then you're going to pump your frac job through a work string, and the cup's isolated. Now, if you're using the cups, those are always active and always isolating as you move up the well bore. So So one of the challenges, if you're using the cups, is what if you're during your refrac, your stages start communicating, and now you dump your refrac back on top of your work assembly, and that can create some challenges. So really your only option here is to try to basically pull up, use the force of the drilling rig, rip off the cups, and just recover your strain. So the other way to do the straddle isolation is use resettable packers. So same overall concept, except for now you have the ability to set and unset the isolation devices. So you run in with your resettable packers, you set them to isolate, then you unset to move to the next stage, reset them, and pump your refrac job through your work string. And now with this setup, if you do have that same scenario where perforations start communicating from the refrac, now you can unset the packers, you can circulate out the excess sand, and then you can recover and move on up your wellbore and continue your refrac. Another option is expandable liners. So with these, this is a very ductile joint of casing. I believe it's typically a J55 grade casing. And so it's just a smaller string of casing that you run inside of your original completion casing. And once you get to the intended depth, then you're going to, you'll run it in on your work string. You'll have the expandable liner, which is that ductile casing string, and then your expansion cone at the bottom. So once you get to the intended depth, you're going to pull up with your work string, drop off that expandable casing joint, or joints, I should say. And then you can see that expansion cone, it literally forces the expandable liner to expand out, touch the old casing string, and isolate. So you're just going to use the force of the drilling rig or workover rig to pull up that expansion cone and complete the expansion of the expandable liner. Then once you've done that, now you have a re-isolated wellbore, and you can go in and do plug and perf operations as your refrac. There's also a couple of options with, excuse me. Sorry, this is getting in my way here. All right, so there's also an additional option to run an additional tubing string with isolation packers. So there's a lot of different ways you can do this. So if we kind of go back to the example I was using before, if it's a very old well, there's perforations maybe every 200 feet, 300 feet, then you may want to run in with these packers, these expandable packers, and try to isolate each of the old perforations. And then once you've done that, now you have a good well bore, and you can go in and do plug and perf between each isolated perforation. So most of the time in this strategy, you're going to actually be trying to isolate the old perforations and create new perforations. But if maybe you're in a newer well that you're refracturing, it's probably not practical if there's, let's just say if there's 100 perforations in the well. If you tried to straddle each one of them, that would require 200 of those isolation packers. So it's probably not that feasible from an economic standpoint. So the other option is to go in with these packers and isolate segments of the well. So you may isolate 3, 4, 5 perforations at the same time, cut off those or isolate that individual section. And then you can go in, you can add new perfs, you can use the existing perfs, whatever your strategy is, and refrac with a plug and perf through that additional tubing string. Another option, and I know this was a very common, common for certain operators, I should say, in the Haynesville Shale, they would run an additional tubing string. So if this was a 5.5 inch completion, 5.5 inch casing on the original completion, then maybe they would run in with a flush 4 inch joint or 3.5 inch casing string into the old completion system. They would pump cement through that tubing string. That would provide isolation on the annulus. So you would isolate the old completion string, and now you have a completely isolated liner again, and you can go in and do a plug and perf job into that smaller new completion for refrac. Then afterwards, you mill out the plugs, just like a typical plug and perf, and put the well in production. Now, another option is to use an additional tubing string with gel. So in this case, it looks exactly like we had before. We run a smaller tubing string inside the liner or inside the original completion. And now this time, instead of cement, we're going to put in a gel that's going to isolate the annulus. So the gel has the same functionality of the cement as far as the isolating the annulus between the new tubing string and the old completion system. You can go in, you refract, do your typical plug and perf work. And then once you're finished, you mill out the plugs and you can spot acid on this gel. It'll dissolve the gel. And now you can retrieve that tubing string out of the wellbore. So the idea here is that you can do multiple refracts with this type of system because you're removing the tubing string from the wellbore. Whereas before, if you cement it into place, then you're probably not going to be, you might be able to get one more tubing string inside of this one if you wanted to do a refract, but then you would have to add another layer of cement. And so at that point, you have to wonder if you're going to find perforations that can penetrate through 3 layers of casing, 3 layers of cement, and into the formation. So you might be lucky and get one more refract, but in a lot of cases with this additional tubing string, that is a one-time refract. So if you want to do it multiple times, the gel may be a better option for you. And one of the caveats with the gel as well, you are removing that additional, excuse me, you are removing that additional tubing string, but you do have to remember that you're fracturing through the original completion again, you're adding perforations to it. So wellbore integrity in the original completion could also be an issue if you try to do multiple refracts. Another option for refract is the reclosable ball activated sleeves. So with these sleeves, once you're finished fracturing, you can go in and mill out the ball seats, and that exposes a shifting profile so that you can use coil tubing or a workover rig to go back and reclose all of these sleeves. So once you've done that, that gives you a couple of options. The first one is you could go in and selectively open each one, fracture, and then reclose to get isolation again. And you just do that for each sleeve. And the other option is you could go in, close all the sleeves to get isolation, and you could do plug and perf refract between the sleeves if you wanted new injection points in the well. Now, another system that's out there is that it's reclosable ball activated sleeves, but you can leave the ball seats intact while you're reclosing them. So, so you go in, you go through the ball seats, you pull the sleeves closed, and once you've done that, then you can drop the exact same balls as you did before in the initial fracture, and you can do your refract that way. Now, the caveat to this system is you're going to be limited to, and it's going to depend on which coil tubing size you have available too, but assuming that you can get about a 2-inch coil tubing unit, your minimum diameter that you can leave in the wellbore without milling out would be roughly 2 inches. So that leaves you anywhere from 20 to 30 stages for this type of system. So a lower number of stages, but a very neat concept as well. Then you have the reclosable coil tubing activated sleeves. So you can go in, reclose all those sleeves. Once you've re-isolated, now you can fracture however you want to with it. So you can do your traditional frac where you're toe to heel. You can do your out of order fracturing like we talked about yesterday, where you're reclosing the sleeves. So the reclosable sleeves give you a lot of different options when it comes to refracturing. But I will throw out a caveat for both the ball activated and the coil tubing activated sleeves. Very few have been installed, and even fewer have been reclosed and reopened. So, I think all the service companies that offer the reclosable sleeves have done an excellent job of testing them and testing them in the lab. But as we all know, the reality is the lab is not the field. And so crazy and magical things can happen when they're sitting in the wellbore, especially for years at a time. So we, in my opinion, they're very much in field trials still. The coil tubing activated sleeves especially have been, more of them have been installed and reopened and reclosed, but there's not a significant case history or volume of case histories on that either. So really just depends on how much they can isolate, if they get complete isolation again, or if they get good enough isolation, and then if they can be opened and reclosed multiple times. But in theory and on paper, that would be an outstanding option for refracturing. Now, I don't know if you noticed it or not, but so far everything we've talked about on refracturing has been in cemented applications. And theoretically, all the option I'm talking about can also be used in open hole refracturing, but you have a couple of different things to consider with the open hole. So let's say, for example, you go in with an expandable liner in a situation that was open hole, and let's just say this is one of the older systems, so maybe this is a 500-foot stage, so 500 feet between each packer. You run in with the expandable liner, you set it, you isolate through tubing, and you isolate completely through tubing. So now you've isolated off all of the old frac ports here, but you still don't have any isolation through this original annulus. So what happens when you go in, you go to do a refrac with plug and perf, you intend to fracture there, but the path of least resistance is actually there. So then you go back in, you isolate your next set of perforations, you've actually already refractured that area. So it is something to consider when you're doing refracs in open hole. Can you get the original annulus isolated, and at least isolated well enough to successfully execute your refrac? And one of the techniques that I've seen operators at least try to do, kind of once again, I consider it in field trials because I don't know that there's enough out there to say definitively that this works, that this works well. But what they'll do is they'll run in an additional tubing string, they'll pump cement through it, but instead of just trying to isolate the new annulus, they'll actually pump cement back towards the heel, and they'll try to let it gravity feed into that old annulus and try to at least get some isolation into the old annulus so that you can have a successful refrac. And hopefully, at least if it works properly, then you isolate your stages properly again. So that was just a really quick overview of the refracturing options. Like I said, especially when you're talking about refracturing selection, it is most definitely a complicated subject. But we've learned a lot in the last 5 years. I expect us to continue that learning curve. And I think that refracturing will be very successful in the coming years. All right, so at this point in time, we're going to shift to the completion comparison. So each of these completion systems, what we've talked about so far and what I hope you've picked up, and by the way, if you're taking the quiz, I would highly recommend paying attention on this slide. So, so first off, we have thousands of runs with each of these systems. So they provide effective multi-stage isolation. All three of the systems have proven that, no doubt. Now, all of the systems, they can isolate with either cement or open hole packers. You can do open hole plug and perf, you can do cemented sleeves. So if you're in a situation where cement or open hole packers is a better fit for annular isolation, it doesn't matter. You can use all three systems with the isolation. All of the systems can also be diverted with multiple or single entry point fracturing strategies. So if you're, you can do single entry plug and perf, you can do multiple entry frac sleeves. So regardless of whatever, if you want single entry pinpoint style fracturing, or if you want multiple clusters trying to cover a larger space, you can use all three completion types. All of them have it set up to where that's an option. And then obviously all of them do require different services in the field, which that can play a big difference as well. So how do we choose the right completion system overall? So we'll start by looking at benefits and considerations. So we're going to use 9 comparison metrics. We're going to use number of stages, stage placement while fracturing, completion design flexibility while fracturing, contingency options while fracturing, services required, operational efficiency, post-frac operations, and refracturing options. So let's start with the number of stages. So with plug and perf, we have a virtually unlimited number of stages. Your the practical limitations on plug and perf are going to be the length of coil tubing and the ability to remove plugs in longer laterals. So that could be a limitation there. Now, one of the workarounds for that is to use a workover rig to remove plugs instead of a coil tubing unit. You can get more weight on bit with a workover rig. Generally speaking, you can get out further in the lateral, and it's easier to remove plugs. The overall process may be a little bit more time consuming than coil tubing, but overall the ability to mill out plugs, it can be easier. And then the other option is to use a hybrid system that's interventionless towards the toe. So this could be a composite plug towards the heel with dissolvable plugs towards the toe. It could be the cemented multi-entry sleeves with the toe, whatever you're choosing there to make it a hybrid system and not have to go out and mill out plugs in longer laterals. With the ball activated completion systems, there is, with the traditional ones anyway, there is a finite number of ball and ball seats. Once again, we're going to use that 4.5-inch casing. That's the most common application for these systems is 4.5-inch casing. Theoretically, you can get more stages with 5.5-inch casing, but because of the nature of the frac balls, the larger they get, the weaker they get. So you're actually not going to add many stages between 4.5-inch and 5.5-inch casing. But if you're using 4.5-inch casing, you can do 40 stages at 10,000 PSI. If you're able to do less than 5,000 PSI, you can do 65 stages. If you're using cemented sleeves, where you have that cement wiper plug we talked about, and you have to be conscious of that 2-inch ball seat diameter, that's going to limit you at less than 30 stage. Or in some cases, operators, that's in their standard operating procedure. They don't want a ball seat diameter smaller than a 2-inch diameter because they want to be able to go in with coil tubing and intervene if something happens. So sometimes their standard operating procedure is to not have a diameter smaller than 2 inches. And if that's the case, this system's limited to about 30 individual stages. Now, some of the newer sleeves we talked about, that's going to be the pump down ball seats with the collet on it. That's going to be the sleeves with a counter mechanism in it. These sleeves, the whole purpose of these sleeves is to offer a virtually unlimited number of stages with little or no diameter restrictions while having the same overall benefits and processes as the traditional ball activated sleeves, where they have nonstop fracturing and very, very efficient operations at surface. And then the coil tubing activated sleeves. Once again, virtually unlimited, but you do have to consider the length of the coil tubing and the ability to function any tools in the long laterals, function tools, locate sleeves, things like that. So, so one of the options to extend the reach beyond that is to use the hybrid system that's interventionless towards the toe. And the most common way to do that is, like we talked the other day, run a single entry cementable ball activated sleeve system at the toe of the well, and then run the coil tubing sleeves within this operating range of coil tubing and back towards the heel. So stage placement while fracturing. So we'll start with plug and perf here. So in this case, there's a fault or some other geohazard that we've realized is in our well after we've completed the well, or at least after we've constructed the well bore. So with plug and perf, it's very easy to navigate around this hazard because until you fire your perforations, you haven't determined exactly where your stage places are or stage placement is. So you just pull up the wire line 200, maybe 300 feet away from that fault, set a plug to isolate, and then you just resume your frac job as you intended. So you can easily skip over a section of the well. if you're using the ball activated completion system and you realize that there's a fault after you've constructed the well bore, then you have very limited option. Really, the only option you can do is drop the ball that corresponds to the fourth sleeve in this example. So you skip over that third stage, and then you just continue your frac job above that sleeves or above that fault. Now, obviously, that's not an ideal situation because the now you have a sleeve and a packer down there that you're not getting any value out of, but it's also better than wasting your time fracturing into a into a fault. And then if you've constructed your well bore with coiled tubing activated systems, your sleeves they are where they are. So the only way you're going to work around with it is once again to just skip over the stages that would be affected and open the sleeves above it and can resume your frac job as you intended. So design flexibility while fracturing, plug and perf has a very unique benefit here because this is just a cemented casing string. So you can do whatever you want with this well bore, and you're not restricted by packer placement, sleeve placement, anything like that. So what that allows you to do, and we'll look at an example here in a minute, but let's just say an operator drills a well, they leave it uncompleted for a year, and then when they go back a year later to fracture the well, their modern completion is very different than before. So maybe when they drilled the well, they were going to take this section of well, put 2 stages in it, 3 clusters per stage, and now their modern completion design is the same length of well. They're going to put 1 stage with 6 clusters per stage. So you can do that. You have complete and utter flexibility to just adjust your completion design based on your current practices. Now with the ball activated system, your completion equipment's set. So if you wait a year or two to fracture this well, there's not a lot you can do, or there's not really anything you can do as far as adjusting your stage placement and stage spacing. So wherever your equipment is set, that's where your stages have to be. Now with the coiled tubing activated system, same thing with the sleeves. Once the completion equipment is set there, that's where your stages are, at least through the sleeves. But with the sandjet perforator, you do have some flexibility. So if you decide that you space the sleeves out too far, you could go in, sandjet perforate between the sleeves and add stages on the fly during the frac job. So you mostly can't adjust it, but using the sandjet perforator in an alternate technique, you could do so. So let's look at contingency options, starting back with plug and perf. If you're fracturing this stage and you screen out, you don't have any diameter restrictions above you. So you can shut down your frac job, go in with through tubing intervention, clean out that screen out, and then resume your frac job as you were intended. So, it really just depends on how readily available a workover rig or coiled tubing is as to how quickly that could be. If you have it on location relatively quickly, if you have to wait 6 weeks, then obviously you're going to have to shut down and come back to that well. The ball activated completion system. So if you screen out while fracturing there, you do have options, but they can be limited, especially depending on where exactly you screen out. So what you can do with the workover rig or coiled tubing, you can run in with a tool that basically mimics a frac ball. And let's just call it let's say you have a 2-inch coiled tubing unit. And so you can mimic the 2-inch ball. You can go all the way down to the 2-inch diameter. You can set it on there. You can apply pressure down the annulus and a force from the coiled tubing and shift this sleeve open and resume your frac job. Now that sounds like a great contingency option, and it probably is in this scenario here when you're only skipping over 1 stage. The problem is, what if the screen out happens in a 65 stage system and it happens on the first sleeve of the well? If you go down to that 2-inch ball seat, that means you're probably losing 30, maybe 35 stages of your well. And so that may not be quite as attractive of an option there. So you really have to look at how many stages will be lost and how many stages you're willing to lose overall to make that decision. Now, if the worst case scenario happens and you're losing 30, 35 stages, or at least more than you're willing to lose, then the worst case scenario option would be to mill out all the ball seats and do an open hole plug and perf for the remainder of the well bore. And then with the coil tubing activated system. So this system, hands down, has the best contingency option. If you're in a situation where you do screen out, it has a unique feature in the fact you already have coil tubing on location at the depth of the problem, with the ability to circulate through coil tubing and through a sand jet perforator and or a circulating sub, and you can wash that screen out back to surface and resume your frac job. So from a contingency standpoint, from screen outs especially, the coil tubing completion system definitely has the best contingency options. Now, if we look at operational efficiency, with plug and perf on a one-off well, it can be very low because between each stage, you're going to have to make this wireline run, set your plug, pull-up hole. You'll have to perforate all of your clusters. And then once you're through with your perforations, then you pull out of hole. And once you're out of hole, then you resume your frac job. So it really depends on how good your crews are and how well, and assuming everything goes well, as to how quick that's going to be. Obviously, it depends on depth, but the general kind of rule of thumb that I've talked to a lot of people about is if nothing goes wrong and if you have a really good crew, that's typically a 2-hour process at minimum. So, if you have 100 stages, that's a significant amount of time. But what we've seen with plug and perf, and to a large extent, this is why I kind of attribute the, or at least some of the success and the shift towards plug and perf in the U.S. is as the U.S. unconventional plays have matured, they've also started pad drilling, and the wellheads are really close together. So they can implement the simultaneous fracturing operations, also known as zipper fracs. And what that allows you to do, you can pump on one well while running operations on the other. So we're going to run wireline on well B while fracturing well A, and then switch it back over. Wireline on well A while fracturing well B, and then just continue that process. And even if it's just 2 wells, that's a huge savings in the fact that your pressure pumping is not sitting idle at least the whole time while you're running wireline, and vice versa. And operators have gotten really good at doing this to the point where some of them publicly state that they have no non-productive time between stages. They always have their frac crew and their wireline running. And in some cases, that'll be multiple frac crews, multiple wireline crews. But assuming everything goes right, it's a nonstop fracturing operation. One of the highlights of the ball activated completion system is the operational efficiency at surface, because just even if it's a one-off well, you're just continuing to drop balls in the correct order. You never have to shut down your pressure pumping. So it's very, very efficient at surface. There's no downtime between stages, assuming that everything goes well as planned. And with the coil tubing activated systems, you are going to shut down between each frac stage. You have to pull to release the packer, move up the well bore, locate the next sleeve, open the next sleeve, and then you begin fracturing. You open the next sleeve, and then you can begin fracturing the next stage. So once again, it's going to depend on the length between stages. It's going to depend on how good your equipment is, how good your crews are. But generally speaking, what I've talked to with people, if it's good equipment and if it's good frac crews.
Kevin, if you want to stop and bring some water, I can cut that from doing the video editing.
Yeah, that's fine. I've got water with me, so.
Okay.
Yeah, I appreciate it. I think I'll be okay. We got a lot of weather changes in Houston, so it's got my sinuses messed up a little bit. Yeah, sorry. Okay, so yeah, the transition between stages. So it will depend on how good your crews are, but the people I've talked to, if it's a really good crew with your coil tubing and pressure pumping, you're looking at about 10 to 20 minutes between stages to unset your coil tubing packer, move up the well bore, locate the next sleeve and open it. And so there is some downtime between stages, but in most cases, it's relatively small amounts. So with the services required for fracturing, obviously all of them require pressure pumping. With wireline, that is a requirement for plug and perf. And with coil tubing, it can potentially be a requirement for plug and perf. It really depends on whether you're doing tubing conveyed perforations at the toe of your well, and maybe if you mill out your plugs very closely after the frac job, you may want to have it nearby location as well. And then, of course, it is a requirement for the coil tubing activated completion systems. But it's never as simple as which services are required for fracturing. You have to consider several things. So are wireline units available? Especially in the international and emerging markets, you have to consider that. Do you have good enough wireline units available or wireline in the country at all? Also, there's always finicky things getting new products through customs. So in some of my past work with international markets, I've seen perforating guns especially get caught up in customs. And the customs in the countries would not release them because they seemed like military grade explosives or something along those lines. So if you can't get perforating guns into the country, then obviously plug and perf is not an option either. Another thing is the right size coil tubing available, and are the well sites accessible to coil tubing. So it's one thing to have the right size coil tubing. It's another thing to be in a mountainous region and not being able to get a large enough coil tubing unit up on location to be able to operate with coil tubing systems or to mill out frac plugs. At least in the stories I've heard and stuff like that, it's going to be a disaster waiting to happen if you go in and try to mill out plugs with an undersized coil tubing unit. So another option is a workover rig. So is it available? Is it a viable option? Can you get it into the mountainous regions or the smaller website or well sites, and mill out plugs that way? And it's also very important to consider the cost of these services because that will play a huge part in your economical decisions as well. Years ago, probably 8 to 10 years ago, I was working on some stuff, and we were trying to get some completion cost comparisons, things like that. And coil tubing units were $40,000 a day in Oklahoma and $100,000 a day, or $120,000 a day in California. So that's 3 times the cost. And especially if you're talking the coil tubing activated systems where it's required all days on location, that can play a huge factor in your overall economics. So with your post-frac operations with plug and perf, if you're using traditional composite plugs, which is still the preferred method, the plug mill out is required. But after you've milled out your plug, you're going to have a full production diameter. And an additional benefit is you also do a clean out run. So you're going to remove any sand and debris that's left in the well after the frac job as well. If you're using dissolvable plugs, there's no post-frac requirements. If they work as intended, then they will dissolve and remove themselves from the well bore in the frac fluid and the production fluids. But a clean out is optional. And at least what I'm observing right now, most operators that are running dissolvable plugs are doing the clean out option afterwards. And most of the time it's for 2 reasons. First, to make sure that the dissolvable plugs are gone, but they also do a clean out trip to remove any sand and debris that's left in the well bore too, to make sure that that doesn't hinder production. With the ball activated completion system, there is no post-frac requirements. You can just fracture through them and start producing right away, but you are going to have a production diameter restriction because of the ball seats. So if that is an issue for you, you can go in and mill out those seats and get a near full wellbore diameter again. And with the coil tubing activated system, if you're using standard sleeves, there's no post-frac requirement. You can put it on production pretty much immediately after you're finished fracturing. And you will have the full production diameter. But the clean out is also optional here. And at least as far as I can tell, most operators do the clean out. Overall, if you're already on location with coil tubing, it's set up to go. Overall, that's a relatively quick trip. It doesn't add a significant amount of cost for them or risk for that matter. So in a lot of cases, they go ahead and do the clean out just to make sure that there's nothing in the wellbore that will hinder production. And if you use the reclosable sleeves and you reclosed them on the initial frac, and once you're done, you have to go back in the wellbore and open the sleeves up for production. Now with the refracturing options, so with diverters, you can use it with all three systems: Straddle Isolation, Expandable Liners, tubing string with expandable packers, tubing string with cement, tubing string with gel. All completion systems can use that, all of those options. With the reclosable sleeves, you have the ball activated systems and the coil tubing activated systems, but there's that caveat there. That's if they're installed. You do have to make plans for that in the original completion and run the reclosable sleeves to be able to have that option. Now, if we look at the diverters from the straddle isolation, you can get multiple refracts, assuming that you maintain wellbore integrity through the refracts. With the expandable liners and the additional tubing strings with packers and cement, you're likely to only get one refract because you're reducing the diameter each time you do one of these systems. With a tubing string with gel, theoretically, you can do multiple refracts, assuming that you maintain wellbore integrity in the original completion. And same thing with the reclosable sleeves, multiple refracts, assuming that the frac sleeves themselves can hold up to sleeve integrity. And then for all three completion systems, if it is an open hole isolation used in the original completion, you do have to consider how effective is the refract isolation going to be. So all of these factors will play in. So it looks like there's a lot of refracturing options for everything, and there is, but there's a lot of factors. It's more than just what can we do. It's planning for the future as well. So this is just everything we talked about. This is just a cheat sheet. All these things that we discussed side by side. So you can screenshot it and have your cheat sheet if that's useful for you. And now we'll go into application comparison. So beyond the benefits and considerations, how do we choose the right completion system for our specific application? And just word of warning, these are general guidelines, and I'll go through an example of exceptions to the rules. So let's start by looking at multiple entry fluid distribution. So if we go back to the 3 clusters per stage and the very basic theories of hydraulic fracturing, if you're pumping at 90 barrels a minute through 3 clusters, that means you're assuming even distribution and you're assuming 30 barrels a minute per cluster, per injection point. But if you're using single entry and want 30 barrels per minute per injection point, because you're only going out of one injection point, then 30 barrels a minute at the injection point is 30 barrels a minute at surface. So, so you don't have to have those high rates to achieve the same thing. So this is a case history from the granite wash. This is 2 wells. Well A is a plug and perf well with 10 individual clusters and 3 clusters per stage. Well B is a coil tubing activated completion sleeve or frac sleeves, and there's 30 of those. So overall, the same number of clusters, or excuse me, injection points, 10 by 3 on the plug and perf well and 30 sleeves. And the spacing is exactly the same. And it's very important to note that it's 165 feet between each cluster on well A and between each sleeve on well B. So a very, very similar comparison as far as injection point spacing was the same. Then you look at all of the fracturing parameters. The variance is very little, if any. So virtually the same frac job, but where you get to looking at the difference is average frac rate. So well A required 99 barrels a minute, whereas well B, you were at 40 barrels a minute. So if you go back to that basic theory, 99 barrels a minute out of 3 clusters, you're assuming 33 barrels a minute per injection point, compared to 40 barrels a minute with the coiled tubing activated sleeves. So arguably, this is a more aggressive frac job on well B at 40 barrels a minute versus 33 barrels a minute per injection point here. But look at our horsepower. Well A required nearly 21,000 horsepower, whereas well B required less than 7,000 horsepower. So that's a very significant difference. That's 14,000 horsepower that was saved on location. Just to kind of give you a reference and an idea, obviously this is going to vary from service company to service company, the size of the pump, everything else, but a brand new pump out of the factory in the US is typically 1,500 to 2,000 horsepower. And once again, that's fresh out of the factory. That's after it gets wear and tear, it lowers. But let's just assume we have 2,000 horsepower brand new trucks. That's 7 trucks plus any redundancy saved on location just by using single entry fracturing. So if space on location is a big deal, single entry pinpoint style fracturing can be a big benefit. So this is also a common issue through several plays in the US, through several plays international. And so what we've got our target reservoir number 1, we've got our completion set in it. Then above it, we have target reservoir 2. So we want to come back and develop target reservoir 2 at a later date. And below it, we have a saltwater bearing zone. So it could be an old water flooded zone. It could just be a brine soaked zone, whatever it is. But either way, between these reservoirs, we don't have any real good frac barriers isolating target reservoir number 1. So if you go multi-entry technique, the problem is, and the risk is, what if your frac job looks something like this? And we can apply diverters and we can apply limited entry perforating all day, but those don't affect the overall rock properties. And that's what dictates how the fracture is going to grow. So there's 2 problems here. The first one is pretty obvious. If you fracture into that saltwater zone and you maintain conductivity, then you're going to produce water, and that's going to significantly decrease the value of your well and increase the expenses of having to dispose of that salt water when it comes up. So that's a pretty obvious issue there. But the second one, and it may not be as obvious at first, but what happens if you breach into target reservoir number 2 and start producing through that? You may get a great well out of it still, but what happens when you go back a year or two, or go forward a year or two later and start developing target reservoir 2 and realize that you've been depleting it the whole time? That's going to cause you issues in the development of target reservoir number 2. And it also probably means you didn't effectively drain target reservoir number 1 either. So overall, in the big picture, that's not a good situation either. Now, by no means am I trying to claim that you have direct control over height with the single entry system, because you don't. It's the same weak point in the fact that the rocks are going to dictate how the fracture grows. But what you do have is direct control over how much fluid you inject into each injection point. It's not trying to distribute through multiple points. It's only the single point. So if you have a pretty decent idea of how your fractures are going to grow, then that gives you better control of your height containment. And you could also do some real-time monitoring, try to make sure that you don't breach out of zone. And if you are about to, then you can adjust your fracture as planned. So no direct control of height by any means, but indirect control of height through the means of single entry point that you're fracturing out of. So wells with longer laterals, 10,000 foot deep, 10,000 foot long. It's actually a pretty standard profile in a lot of the mature U.S. plays, but in emerging markets, that's still a pretty long well. So the challenges with these longer laterals is first off, locating wireline and coiled tubing units with enough length. just to kind of give you some reference there. In the U.S., each state is going to dictate its own weight requirements on the highways through their Department of Transportation. But in Texas and New Mexico, where the Permian is located, to meet the weight requirements for their Departments of Transportation, a brand new coil tubing unit, the newer ones that are 2 5/8 inch diameter, fresh out of the factory, would be around 26,500 feet. So, and that's rolling out of the factory. As soon as you start using the coil tubing, you start getting fatigue on that coil, then you're going to, or on that tubing, then you're going to have to cut off 100 feet at a time, a couple hundred feet at a time, maybe a few thousand even. So even if you're able to get into a 20,000 foot well, total depth well, then you may have issues trying to locate a coil tubing unit that has enough length to do so. Running through tubing operations can be a challenge. Locating and functioning downhole tools in these long horizontals. And then, of course, milling out plugs or ball seats can be challenging too. So all of these challenges point us in the direction of a ball-activated completion system or some sort of hybrid system where you have dissolvable plugs at the toe or the cementable ball-activated sleeves at the toe, something interventionless at the toe beyond the reach of coil tubing. And this is why I think that the ball-activated completion system had a lot of success in the U.S. Bakken in the early days of unconventional development, because in 2008, operators in the Bakken were starting to drill this profile of 10,000 long and 10,000 deep. And in 2008, the technology of coil tubing, the availability of coil tubing, all the additional lubricating fluids, mills, motors, the technology just was not there of what we're doing today. We can mill out plugs very, very efficiently today, in the right application anyway. But then back then we weren't able to. So that's why it made a lot of sense for the ball activated systems in the US Bakken, because they didn't have to go in and intervene afterwards. They would drop balls to frac, put the well on production, and that was that. Now, we also have an extended number of stages. So the next two examples, these are obviously going to be very relevant to where you're at, as whether it's a low number of stages or an extended number of stages. But nonetheless, using this example here with 40 stages and the next one with 5 stages, I think you'll get the point. It illustrates, how different each frac design can be there. So in this example, we're going to use a 40-stage system. We'll assume 1 hour per stage in the frac plan and no operational issues. So if we have the ball activated completion system, it's 40 hours total time to stimulate. So that's going to be 2 days with a 24-hour crew, 4 days with a 12-hour crew. Now, if we're looking at plug and perf, we're going to have to make an additional assumption, and we'll assume that we're going to have 3 hours to run in with the wire line, set the plug, perforate, and then pull back out a hole between stages. That means it's 160 hours total time to stimulate, which means 7 days with a 24-hour crew, 14 days with a 12-hour crew. So in this example here, the ball activated completion system has a clear advantage over the plug and perf systems, because you're taking the frac cycle time from weeks down to days. Also, a low number of stages. So same assumption, but now we're going to look at a 5-stage job. So with the ball activated system, it's 5 hours total time to stimulate. That's a day with a 24-hour crew or a 12-hour crew. Plug and perf with that same 3-hour assumption between stages, that would be 20 hours total time to stimulate. So that's a day with a 24-hour crew, 2 days with a 12-hour crew. So in this case, it's virtually the same. There's not a significant difference in the operational efficiency at surface. So you really would have to look at the local economics and regional economics to really decide which one is the best completion for that well or for that area. So if we step back and look at the bigger picture, so the appraisal phase is in the asset life cycle is when an operator has basically obtained new acreage. So they don't know anything about it really. Their objectives are going to be different than any other time in the asset life cycle. And their objectives are going to be to gather as much data as possible and just overall to learn that formation in that field. So there are certain risks associated with the appraisal phase. First off, you may not know exactly how you want to complete this well as soon as you're done drilling it. You may want to take your time. You may want to analyze things that you saw during the drilling process, run some additional logs, things like that, and may just need to take your time and apply a little bit of science. Also, it's a much higher risk of poorly drilled wells and screen outs during the frac, because once again, you don't know this formation, you don't know how to drill it yet, you don't know how to fracture it yet. So what are your ideal completion requirements there? First, a system that would allow you to adjust stage placement on the fly during the frac job and complete it however you want. A completion with no increased diameter with the completion tool. So essentially no packers, no sleeves. So it's easier to get into the wellbore, even if it's drilled poorly. And a full diameter inside of the completion so that if you do have a screen out, you can go in with through tubing tools and help recover from that screen out. So that points us in the direction of plug and perf. Now, once they've learned this formation and they transition out of the appraisal phase, then they go into the development phase. The objectives are a little bit different here because now they're going to focus on cost savings, efficient operations, and maximizing their production. So what are our completion options? First, we have the ball-activated completion system, the highlights being the nonstop fracturing, the improved logistics, and the overall efficiency with a single entry system, as well as pinpoint style fracturing. But maybe you're in that area where the formation is just, it's not homogeneous. It's very heterogeneous. There's a lot of variance. You can't really dial in your frac recipe and you screen out frequently. The coil tubing activated system may be a better bet because of the contingency options with the screen out. Or if you're in that situation where height containment, because there's no good frac barrier between zones that you don't want to fracture into, that gives you some options there. Or if you're in a situation where you're short on space with your location and need to reduce horsepower by going single entry, the coil tubing system may be better as well. And then, of course, plug and perf. Plug and perf is hands down still the most common completion system ran out there in these applications. And it was the original completion system that unlocked these formations as well. And throughout the years, we've significantly improved everything, especially the inefficiencies at surface, by being able to apply the simultaneous fracturing operations, aka zipper fracs. And one of the big benefits now, especially since the 2015 downturn, is the flexibility of stage placement during the frac job, because we can allow that well to sit for 2 years and then adjust it to our modern completion design when we get time to fracture it, or when it's time to fracture it. And there's always just going to be scenarios where one system makes more sense in certain areas over others. So when I was working in the Northeast, in the Marcellus, Northeast U.S. in the Marcellus, one of my customers, they've been running plug and perf for over a year. We were talking with them. They really wanted to increase their fracturing efficiency at surface. So they tried 15 wells with the ball activated completion systems. We followed up with them. They went from 7 to 9 days with plug and perf to fracture plug and perf to 1 to 2 days with fracturing the ball activated sleeves. So they placed a large order for the ball activated sleeves. Oh, and by the way, their production was the same, no better, no worse, same per completion system. So they placed a large order of frac sleeves, and about 2 weeks later, they called and canceled the order. What had happened in between that 2 weeks is they lost their water supply. So now they did not have enough water to fracture more than 2 stages per day, and which means that the ball activated completion system no longer had the benefit of nonstop fracturing. So when they sat down and did the economics, the nonstop fracturing wasn't a benefit. Plug and perf was the clear winner there from an economic standpoint, especially. So there's always going to be those local challenges there. So once again, let's go back to this slide here. I want to remind you that these are general guidelines and there are a ton of exceptions to them out there. So I was presenting this slide or this course in Canada within the last couple of years, and I had a student come up to me afterwards asking about this slide, and he said, we're looking at the appraisal phase, but you're telling me that we have to do plug and perf, but my company is going to run with the ball activated sleeves. So, like I said, I reminded him, well, those are just general guidelines. I'm not saying that that's a hard and fast rule all the way around. So we went and had coffee and discussed his application. So this was a very interesting application. It was a play in northern Canada. They only have access to it in the wintertime. They wait till it freezes up the marsh so that they can get equipment out there. And they only have access to it 3 to 4 months a year. So we sat down, we talked about this, everything. And I said, well, okay, I've identified these 3 as your primary risks. So let's go through them. So first off, do you know exactly how you're going to space your well? Are you going to do any science? Are you doing geometric spacing? And he said, no, we're doing completely geometric spacing. It's already been set. There will be no changes to it. So risk number 1 was not an issue. So risk number 2, poorly drilled wells. I asked if they had any experience at all. And he said, yeah, we have drilled 8 wells there, haven't really had any issues. So overall, they've arguably figured out how to drill these wells. So that's not much of an issue. So with screen outs, first thing, do you have coil tubing on location? Because I suspected they would, because you're not going to wait months for coil tubing to arrive if something goes wrong. So of course, when they go out there, they do have coil tubing with their crews, and it's sitting there on location. So the other factor was, well, if you're going to use the ball activated system, how many stages do you have? And it was less than 30, which means that due to the coil tubing size and the less than 30 stages, coil tubing can enter that well bore and do intervention if a screen out occurs. So all of a sudden, screen outs aren't near as much of an issue as they would be. Now, obviously, when you only have access to a well site 3 to 4 months a year, surface efficiency is critical. You don't want to be fracturing for a week with plug and perf when you could be doing 1 to 2 days with ball activated systems. And, once again, that's all relative, because there were so few wells, they were not doing pad drilling. They were not able to do zipper fracturing. So keep in mind that we're talking about one-off wells, and the efficiency is much, much higher with ball activated systems in that case. So we looked at all, when you sit down and look at that application, the ball activated system is hands down the way to go. It makes all the sense based on the risks and everything that they have in their particular application. And the additional benefit is this operator had other fields throughout Canada, and all of their people, all of their crews, they had experience with the ball activated completion system too. And there's a lot of value in those intangible assets of your people knowing how to operate those systems and things like that. So that just further illustrated the point that the ball activated systems really made sense for their application. So I get asked pretty frequently, do we have it all figured out? And in my opinion, absolutely not. Especially since 2015, since the first downturn hit, and now the second really bad downturn with the pandemic here in 2020. A lot of decisions are being made based on economics and downturn economics, and it's important not to lose sight of that. So we have to consider the effects of the downturn on our completion decisions. And so we'll look at a Bakken example. So if you go back to 2013, 2014, the state of North Dakota required Bakken operators to, they had 1 year between finishing drilling the well to fracturing the well and putting it on production. When the downturn hit in 2015, they extended that to 2 years. So there were several prominent Bakken operators that publicly stated, we will continue drilling so that we can hold our leases, but we will not be fracturing wells and putting them on production until we see oil prices we like, or until we have to after that 2-year period. So their overall strategy was to hold wells for 2 years before fracturing them and putting them on production. Now, it's very important to consider because when you're with completions, especially downhole completions, it's a little bit interesting because anything that's a wellbore construction actually goes on the drilling AFE. So the way most U.S. operators are divided, they have their drilling AFE, completion AFE, and production AFE. Everything done by the drilling rig is the drilling AFE and goes on the drilling budget. Well, wellbore construction is done with the drilling rig. So if you have cement, that's with the drilling rig. If you have sleeves, that's with the drilling rig. So you have to factor that in. So if we look at each of the completion systems, they virtually require the same casing, so there's no real expense there, no advantage there. And before I get started too, these are estimated numbers based on large quantities, based on downturn pricing. So don't shoot the messenger. Don't quote me on these prices. Don't go and quote your service company on these prices. These would be really good prices. So take the pricing you have in your local area and do this exercise for yourself if this is applicable for you. So if you're cementing a 10,000 foot lateral, it's about $50,000. And these were numbers that I tried to be as accurate as possible, a general range for the 2015 timeframe, by the way. 50 ball activated frac sleeves. If you assume that they're $3,000 each, that's $150,000. 50 open hole packers. If you assume $3,000 each, that's $150,000. And if you did a 50 coil tubing activated sleeves and you assume $3,000 each, that's $150,000. So our wellbore construction cost per well, per completion type setup, a 50-stage plug and perf well would be $50,000 for the cement. A 50-stage open hole ball activated system would be $300,000 for the sleeves and the packers. A 50-stage coil tubing activated system would be $200,000 for the sleeves and the cement. A 50-stage open hole coil tubing system would be $300,000 for the packers and the sleeves. And a 50-stage open hole plug and perf would be $150,000 for a packer or for the packers. So if you're an operator and your strategy is to delay fracturing and production as long as possible, plug and perf is the clear choice here. I mean, you're saving millions of dollars in less than 10 wells. And at a time where cash is king, obviously that's critical to do. So now from a wellbore construction cost, it really makes all the sense in the world to run plug and perf. Why would you possibly run anything else if you're going to delay fracturing and producing? Now, the other kicker that I think was largely by accident, this is not a 50-stage plug and perf well. Now, all the other ones, the sleeves and the packers are set into place, and there's not much you can do with them. With the cemented liner, that can be a 50-stage plug and perf. It can be a 25-stage plug and perf with more clusters. It can be a 100-stage plug and perf. You really still have the flexibility to adjust to your modern completion design. So that's another additional benefit with that wellbore construction design. So other downturn effects to keep in mind. When a downturn hits, cash is king. The primary objective is to break even on the well. Services are cheap and readily available. And, there's also a human nature aspect of it as well, where people want to keep people working. So they'll lower their prices and keep people working. There's also a lot less tolerance for failure because people are afraid they'll lose their job. And so what that leads to is not a lot of experimentation with new completions. And the interesting dynamic there is a certain level of failure is tolerated with traditional completions. So if a completion engineer has issues with plug and perf, but they've been doing it for 3 years, if a plug presets or perforation doesn't fire or any other operational issues, there's a certain level of failure tolerated. As long as it doesn't happen too much, it's just expected. We're going to have issues in the field occasionally. But if that same completion engineer tries out a new completion system and it fails, then they're afraid they're going to lose their job because of it. So because of that dynamic, it doesn't always lead to innovation with trying new completion systems. Now, none of this is necessarily a bad thing. Keep in mind, especially, and really this is throughout the world, we have record initial production in these wells, in these unconventional reservoirs. But there's a lot of things to keep in mind with that. First off, record amounts of fluid and sand have been pumped into these wells. What we're doing today is not even close to doing what we were doing in 2014. Once the prices of fluids and proppants have lowered after 2015, operators started experimenting more and more. And so these are a lot different fracs than what we had before. And just overall, because of that, the completion strategies today, they can't be compared to before the downturn. And another key factor, you have to remember, the core acreage is being developed right now. So what I mean by that is the best of the best acreage, the acreage that operators know will perform and they know they can break even on. That's what they're doing. So they've dropped off the tier 2 and 3 acreage and focused on their core acreage. So by default, that's going to lead to record initial production. Now, tying it back into the fracturing itself, the downhole completions into the fracturing, it's important to remember fracturing logistics. Besides the pressure pumping, what other services are required for the job? What are the costs of those services? And do the nonstop fracturing operations have any benefit? And that's with the ball activated systems or with the zipper fracturing with plug and perf as well. Your fluid displacement. How accurate the fluid is placed is directly dependent on the completion system, whether it's single entry or multi-entry. And then the effect of the completion. The type of completion will directly affect the frac job because your equipment that you have downhole can limit your pump rates, slurry concentration, pressure ratings, and other parameters. You don't want to design a great frac job and then not be able to execute it because you don't have the right equipment in the wellbore. And then to bring it all together and tie it all in, drilling, completions, fracturing. So drilling directly affects the wellbore completion. When you're drilling the well, you're determining the size of the wellbore and the casing. So you have to be sure that that's compatible with your completion design. And if you drill poor quality wellbores, that's going to have a huge impact as well. First, it'll be difficult to land the completion at the intended depth if you can't get it into the wellbore because it's drilled poorly. And also, if you're going to have difficulty achieving annular isolation with cement or open hole packers if the well is drilled that poorly. So yeah, it all depends. Just to give you an example, when I was in the Marcellus, one of my customers, they decided to cut corners on drilling cost. They hired the cheapest directional drilling company that they could hire, and ended up costing them in the long run because they could not get 5.5 inch diameter casing into an 8 3/4 inch open hole because their wells had a ton of undulations, a ton of spiraling in it. And they ended up having to do a reamer run to get the casing in the wellbore, even without packers and sleeves on it, just a cemented casing string. So they ended up paying more than they intended by cutting cost. And to close it out here, this is almost a repeat of last slide, but once again, very, very important. Your wellbore completion directly affects your frac design because you control the flow area of the completion, pressure ratings of the overall system, and how much control you have over the fluid displacement. So very important to make sure that what you're doing with your wellbore construction, with your wellbore completion is compatible with your frac design so that you can execute it as you want to, or as you intend to. So that's it for this course, for today and this course. So what I hope you've learned through this course is there are 3 viable options in the unconventional plays. It's very easy and people do this a lot. In my opinion, it's a gross oversimplification to say, well, the US is running 95% plug and perf, so plug and perf must be the best completion system. I don't think that that's necessarily the case. It's going to very much depend on everything. It's because of the dynamics of the downturn, the dynamics of zipper fracturing, things like that, why it has been the most effective and the preferred completion in the US. But that's not always going to be the case throughout the world and throughout other places in the US for that matter. So that's what I hope you take from this, is that all three of these are viable options. It really just depends on your situation as to which one is best for your application. So thank you. I hope you enjoyed this course. If you did enjoy the content, don't forget to subscribe to my YouTube channel. And you can go check out my website, uog.training, for additional free resources as well. So at this time, I'll open it up for questions and answers.
Thank you very much, Mr. Burton, for such a wonderful and informative session. I have several questions to you from our audience, and I want to read them out. So the first one is, how many years can the reclosable sleeves stand within a production well without being eroded or corroded?
Yeah, so and that's why I threw out the caveat with the reclosable sleeves is it's really and truly anyone's guess. Like I said, I think the service companies have done a really good job of testing them and testing them as much as they can in the lab, but it's just different when you have them in the field for 2 or 3 years. Just to kind of give you some reference, I think the longest amount of time I've heard so far today, or in today's times, is about 6 months has gone by before they tried to do anything, open or close them again. And at that point, they did work as intended. You know, once again, it's relevant, but it's not exactly the same. I'll just kind of give you an example of multiple things through the year. So the pressure activated frac sleeves. I've come across a lot of applications where, when I was an application engineer, where all of a sudden someone would reach out and say, hey, how long will that sleeve last? How you know, can I still open it? And normally we're like, well, how long has it been in the well? And I've heard of those sleeves working after 2 or 3 years sitting in the well bore. So it's really anybody's guess, but and we do need more field trials to kind of approach that with more certainty. But overall, I think the designs are pretty good to try to withstand those conditions.
Okay, thank you very much. And here is the second question. How could I make sure that the diverter I pumped is placed at the perforation that I want and didn't go to another perforation?
Yeah, so that's that is the problem with it, is especially when you're looking at refracturing applications, it's not really all about making sure that it goes into one perforation over the other. It's about assuming, even if it's not in the right order, even if it's not heel to toe or toe to heel, as long as it's continuously breaking down additional perforations, that's really the objective there. So, you know, in my image that I showed, I just kind of showed heel to toe because theoretically that's how it would break down, at least from a friction standpoint, through the well, because the perforations closer to the heel would have less friction, which means that they have less or a path of least resistance because of friction in the pipe. But I think we pretty much know that that's not the case. It may be that one of the perforations in the middle of the well is breaking down, and as long as it breaks down and then the diverter hits that one and forces another one in the well bore to divert or to break down, then you're still achieving the same objective. So especially in the refrac app or application, it's not about doing them in the correct order. It's more about making sure that they all break down and get a refrac through them.
Okay, thank you very much. There are no more questions for the moment. I think we can wait several minutes while I'm telling an important message and reminder to each participant. So please don't forget to take your quiz after the session or Google Classroom. That will be available over some time. Also, don't forget to subscribe on PyPetra YouTube channel to watch and recap recordings of today's and all other past sessions. And of course, follow Arab Oil and Gas Academy Facebook page to see and not to miss all details about these and other upcoming courses. And you may ask your questions there. Also, there will be posted information about our upcoming exam. I'm reminding one more time that it will be on 27th October, Tuesday at 2 p.m. and at 8 p.m. Egypt time. We have a third question, and it says like, can I test each stage of how many barrels of oil can it produce?
Yeah. So testing each stage is pretty tricky. Theoretically, you could do it with a PLT or production log. The main issue with the production log, at least the way they're currently ran, is it's really a snapshot in time, which means literally you can go in and measure it, and it can change as soon as you pull out of the wellbore. So that kind of gives you limited information. The other ways to do it, you could monitor with fiber optics or tracers. And what they with both of those, it's not as much a count per barrel, but it gives you more of a what am I trying to say? It kind of gives you an idea of percentage of distribution, if that makes sense. So instead of giving you an actual count, it gives you a good idea of what percentage came from what stage. If you have enough diverter, or excuse me, I hope I didn't say diverters earlier. Tracers is what I was trying to say if I said it. So tracers, if you have an individual tracer in each stage and you can identify, then you can say, well, I've got, a percentage from stage 1, a percentage from stage 5, a percentage from stage 10, and get a pretty good idea. And then once again, with the fiber optics, it does give you some monitoring as well. So neither of them are necessarily a direct measurement of volume, but it gives you a good direction on how to estimate volume.
Okay, thank you very much. There are no more questions. By the way, here is the last chance for audience to ask your questions before final exam. So we can wait 1 more minute, and if there were no more questions, we can finish the session.